Before we start, let me just give you an introduction to today's speaker. So Zhimian is currently a research associate at the University of Cambridge. And his general research interest falls in process systems engineering and application in digitalization and sustainability analysis of chemicals and energy sectors. So he finished his bachelor degree in Nankai University and Tianjin University in China, and he got his master degree from Delft University of Technology. And he also got his PhD in process systems engineering from the University of Cambridge. And in the past, he undertook some research visits at Imperial College and Aachen University in Germany. So today, Zhimian will talk about his research on integrating emerging technologies with traditional industries for climate change mitigation, a multi-scale systems engineering approach. So yeah, please, Zhimian, the floor is yours.
Thanks, Hongyu. Thanks for the invitation and the kind introduction. Hello, everyone. I'm Zhimian. I'm glad it's my honor to present my work during my PhD and postdoc. Yeah, for today's, do you see the? Oh, I guess I saw something. Sorry, I just need. Okay. Yeah. No. Okay. Yeah. For today's. Yeah. I will.
We cannot see your slides now.
Okay. Sorry. I think I saw some. Okay. Now
you can see.
Did you say like here something like presenting and stop? Okay, now it's gone. Okay, great. Yes, so I will just briefly talk about my academic journey. From 2010 to 2014, I did my undergraduate study in China. Basically, it's joint program for the chemistry study in Nankai University and chemical engineering study at Tianjin University. Afterwards, I came to Europe. The first stop is the Netherlands. I did my master program at Delft University of Technology. And in between, I did a research visit at Imperial College for the reactor modeling stuff. And then from 2017 on, I started my PhD in the UK at the University of Cambridge. And in between, I went to Germany for a short visit, specifically in the field of process system engineering. And for today's topic, I'm going to talk about like okay, sorry, today's I'm right here. There's something. Yeah. I'm going to talk about the start from the feedstocks and energy transition. Energy transition probably is something you're familiar, and I will focus on more about like feedstocks transition, and then I will introduce the methodology, multi-scale system engineering, and with this, then following by 2 case studies. Finally, we'll give the conclusion and outlook. Currently, the carbon-based industry is unsustainable. So the way is like a linear production way, start from fossil fuel. You know, fossil fuel is not renewable, so the whole storage is decreasing. But in between, when they produce like some product like plastic fuels, that will also cause some greenhouse gas emissions. So this linear way is not, of course, is not good. So to tackle this challenge, what they do is like normally people do like it's like 3R, like reduce, reuse, and recycle. That's the kind of generally environmental engineering guys doing. And from a perspective of chemical engineering, what we are doing is like we are trying to do like kind of carbon carbon capture technology, and also trying to develop like renewable carbons like biomass. And that's the two case, and will be like kind of two case study I will talk about later on. And another thing is like probably you know it very well, is like for net zero, when we talk about the greenhouse gas emissions, talking about greenhouse emissions in different sectors, we can see like around 75% of greenhouse gas emissions come from the energy sectors. So net zero to a large extent is like energy transition. And energy transition can be achieved from like two sides, from the supply side to like to transition to like renewables, and the demand side is to like hydrogen economic or electrify kind of industry sectors, heating sectors. And but the things like the reason why wind like carbon capture technology is like for the short term, I mean maybe not like in EU, Norway, but in like fossil domain regions like in Germany or in China, still need like use the coal or gas for the power generation, and then to decarbonize these power plants, and we need like kind of a carbon capture technology to reduce the greenhouse gas emissions. And then talking about like the methodology we are going to use, like that's kind of multi-scale system engineering. So basically that's kind of different skills. First in like lab scale, we're trying to find like innovations can change the world or change the whole carbon transition and energy transition solutions. For example, carbon transition is trying to convert CO2 to like fuels products. We develop like in chemical engineering, develop like by like a photo catalyst and electricity or some novel catalyst to achieve this step. And also for the energy sectors, try to doing something like controllable nuclear technology. And then in the process development, we're trying to do like, like in the kind of process design, we are trying to develop like reaction, separation, and recycle, trying to develop a good, robust process. And then in the whole like supply chain level, we're going to the regions and the global. We're trying to do the overall system engineering. And finally, we will talk about like sustainability, then we should like follow subject to like economic and environmental constraints or objectives. But today's because my field is kind of chemical engineering, most of my work is focused on like process development, and that specifically is system engineering field is called process system engineering or PSE. Specifically, PSE is kind of you can consider it's kind of a tool. Like this kind of tool is what this tool can be do is can facilitate like scale up decisions from lab scales to like industry scales. Then we will do is like digitalize it like this process, like chemical process to like current like machine learning technologies that eventually we will do like optimization. And then for that we will just go back to validate the model and also to accelerate the scale up decisions. And such a methodology, I published these papers in like LSE journal and chemical engineering journal. That's mostly for the methodology. And with this tool, we are trying to solve some problem. The first case study is what I was doing during my PhD to digitalize and optimization of carbon capture and utilization. The full chain for the carbon capture technology actually is called like, you probably know, like carbon capture, utilization, and storage. So basically what that means, like for the carbon source, normally, for example, flue gas in the power plant, Then we capture it. Capture means to concentrate the CO2 concentration from like 50% to like 90%. But the captured CO2 is not an end. We still need to like deal with it, further deal with. One way is to storage this CO2 underground. That's called a storage way, or normally we call it CCS. The second way is trying to convert the captured CO2 to like a fuels product or like a cement or plastic. And today's talk, we are trying to focus on this captured CO2 to like a fuels product. That's the system boundary in this case study. And another thing is we must be understand is like such a way also needs energy, and this energy also can cause CO2 emissions. Let's also introduce the research questions. Just now we talked about like net zero can be equivalent to like energy transition. Energy transition technically should be like fossil fuels to renewables. And the reason why we use the carbon capture technology is like we try to decarbonize the fossil fuels. But currently in academics, especially for the CCU field, normally people consider is like general assumption is like academics like try to assume they will produce hydrogen from like wind or solar and wind for the electrolysis to get the hydrogen, and the hydrogen combined with CO2 to convert to the fuels. But as we know, this kind of renewable energy can be converted for the electric car and the heat pump, or directly go into the grid. So, and also people mention like the decarbonization efficiency to above routes are actually much better than the below routes. So here is like let's go to like a more realistic way. We just say, okay, without the renewable inputs, we want to say like whether the CCU can reduce the greenhouse gas emission or not. And also if this can be reduced the greenhouse gas emissions, then what will be the optimal strategy? So under such a research question, we designed such an industry park. In this industry park, we include like two natural gas power plants and with two like carbon capture technology. And this capture technology will capture CO2 will be converted by the fish chops and the methanol synthesis to get the fuels product. As you see, like here, the CO2 conversion needs the hydrogen, but the hydrogen comes from the steam reforming. So there's no once again, I just mentioned there's no renewables input. And we try to optimize the whole like industry park or the whole system. The objective can be reduce the greenhouse gas emissions and also maximize the profits. And this is the decision variables we can change. For example, for the PIC, we can change like the pressure and duration for each stages, and also for like how we distribute the CO2 to the different pathways. Like ZFT means the portion of CO2 going to the FT routes, and the 1 minus ZFT means like going to the methanol pathway. And also we consider like part of heating can be provided by low carbon electricity. And when we try to optimize these things, we just did like a process modeling for each sectors. For example, here is like for each sector, there's a tailored simulators. We try to simulate the subsystem, but so we come across some optimization challenges. You can see like for a subsystem, they have a different simulation platform, and also with this rigorous simulations, actually one evaluation can be very expensive. So our way is trying to do using a kind of machine learning based model to represent those systems, and then with this machine learning based models can achieve like the the overall system at one platform, and also it's cheap for the optimization evaluation. So that's the overall framework for the optimization. Like level one is like still we build like a rigorous model by like a rigorous commercial simulators, and in level two we digitalize the whole system by the machine learning. And then in level three we do like a surrogate based optimization, and eventually we also validate the results by like in a commercial software for the final validation. And this is the kind of results how we do the multi-objective optimization. You can see like a first iteration means like when we don't do any optimization, you can see all of the result is for like one result is one objective, the x-axis is like a greenhouse gas reduction, and the y-axis is like the profit, and the red point is kind of available results, and the blue circle means like the best case. When we're doing like optimization after 5 iterations, 10 iterations, and eventually we stop at 500 iterations, we think that it's very difficult to improve further. And as such case, you can say when we try to pursue very large, very low greenhouse gas emissions, the corresponding like economic gain or the profit for the industrial park actually is negative. So basically that means the whole industrial park losing money. Well, if we try to pursue a very high profit, like here, actually we can find like the greenhouse gas emission reduction is negative. That means to reduce such a greenhouse gas emission and to convert this CO2 to like fused product, the energy actually cause more greenhouse gas emissions. So basically, the CCU basically actually increase the greenhouse gas emissions. If we check like the reason why, we can find like we select 5 points that you can see like on the left side. That means that have a more Fischer-Tropsch product, means more like gasoline and diesel. That gives more profits but cost more emissions. And on the right, there are more methanols, and that means gives more reduce more emissions. And also it means like use more like CCS electricity. So go back to like the previous question, can optimization basically without renewable inputs, can CCU reduce the greenhouse gas emissions? The answer is an optimal CCU is capable to decarbonize the power plant, but not at the maximum profit. And also you already see like you still remember without optimization, basically random like design, actually CCU can cause more greenhouse gas emissions. That's really bad. So basically you try to use the CCU to reduce the CO2 emission, but actually it costs more. And if you are interested in this digitalization technology, you can refer to the first barcode, and the whole optimization problem can refer to the second barcode for my published paper. And the second case study is about like it's about the biomass conversion, and it's basically trying to scale up the lab scale things. It's basically start from the kind of biomass. We try to produce like cellulose nanocrystals. Basically, it's kind of a high value added products and have many applications. But so far there are very limited research on this field about the environmental impact, because this production is a kind of emerging process, and the information is very limited. But so far they are like for this manufacturers, they have spread all over the world. The largest plant is like in Quebec, like in Canada, and also some like pilot plants in like other European countries and in Asia. Firstly, we try to look at this process in like in a Quebec. They have like a largest plant. So basically, this process actually very simple. Start from the cellulose, and then finally we try to produce the CNC. So that's the product. And in the process, we need to like add the acid and water, and eventually we need like sodium hydroxide to neutralize the waste stream to pH to 7. And we are considering like a circular design to recycle the acid and water. And in this way, we can reduce the acid and water use and also reduce the sodium hydroxide. But the cost is that's increased energy consumption. Then we try to do like a life cycle assessment to check like environmental impacts. And here's the result we found, like basically the circular design shift like environmental impacts from the materials input to energy. You can see like this is no acid recycling. They have a lot of inputs from the materials like sodium hydroxide. Then when we recycle more acid, then we can see there's a lot of burden from the electricity. And also we found actually the partial acid recycle actually is the best, because like if you full acid recycling, like 99% is kind of for extreme process design. And we also think about like how to arrange this like a plant, like a production plants in different region. For example, we already consider like that's in Quebec. If we consider this plant in like in Alberta or Wisconsin in the US or Sweden, Nordic countries, and also in Tianjin in China, where we see the result again. So Quebec is kind of the results I showed before is here actually. You can see like currently like if we put this plant like in other countries, then the results can be super different. And that's kind of existing pilot plant plants. So basically that's kind of benchmark is like 30 to 50. So that means if in low carbon regions like Norway or Sweden or Quebec may consider like extensive circular design or recycling design, but for the fossil domain, the regions like in Alberta or like Wisconsin or Tianjin actually benefits from limited acid recycling design. So that's related to like the regional energy profile. Actually, you see like Quebec have a lot of hydropower, and Sweden, you know, like have a lot of hydro and nuclear. But in Tianjin, for example, it's have a lot of coal and but here these results we already see like because this work we collaborate with Canada company like in Alberta. They already developed a very nice, promising citizen product. Then they try to expand their business. So they ask like, okay, should we choose Quebec or Sweden? Because like you see like in Alberta, energy consumption still couples with greenhouse gas emission. But for these two region, actually energy consumption decouples with greenhouse gas emissions. And we see like, okay, that we consider not just greenhouse gas emission, but we also consider other impact like water, land use, and acid potential. You can see like when we put this factory in like Quebec, actually other of the environmental impacts become better, but for the water, actually they are actually increase more water burden in like in Quebec, but in Sweden, all of the impact category become going to the good direction. So here is the take-home message. I'll say like a life cycle assessment supports decision making for the sustainable scale-up decisions, and from the bottom-up perspective, this yeah. Hello, did you call me?
No, there is no question. Please continue.
Yeah, okay, sorry. So basically here, the energy transition should be go to the diverse renewables, but it's better than relying on singular energy solution. So basically, that's a kind of overall, it's like when we go back to the circular carbon economic, all of the pathways there seems cannot avoid like energy consumption, and that energy consumption really depends on the regional energy profiles, like what's the energy come from, and then eventually that overall system analysis can give like how the greenhouse gas emission is reduced or not, and then that's the final conclusion. Especially for the fossil domain regions, the decarbonization technology is preferred not be energy intensive, and also it's for the evaluation criteria should it's better to develop like diverse criterion, and the methodology we are trying to develop is trying to build kind of process modeling, and then that will be super different from the result of linear scale up lab scale innovations. And also what we show is like a machine learning accelerates the evaluation of the large system, and also we try to say like a multi-objective organization or the multi-correct decision making actually can support the conflicting decision making process. And yeah, that's overall what I want to show for today.